Last time we discussed the inverter ellipse equation. We started out from the inverter model for the converter, resonant inverter model, prepared for the resonant converter. Okay? So from that model, we applied the Thevenin's equivalent form, and this is the Thevenin's equivalent form of that inverter model. This is open circuit voltage source, dependent voltage source, and this is short circuit output impedance of that inverter model. So from this model, we derive the inverter ellipse equation. Okay, I'm repeating two previous slides. Okay, first one is this one. So assume you are looking into this circuit from this point. So you are seeing this relationship between V and I. Through this, there is only resistance, which is this. Okay, this is the equation. This concept is similar to the load line concept in conventional amplifier, audio amplifier analysis. Second one is you are looking into the circuit through this channel. So this voltage V is the same voltage here. This current is I, and this current is I, but I used the different color to conceptually differentiate to set up this voltage and current. Okay. We'll prove this. The relationship between V and I, magnitude of them, is expressed like this. This is the equation of ellipse, and we call it inverter ellipse equation. So it is written like this: V magnitude squared and I magnitude squared, and this is VOC, which is open circuit voltage. Assume this voltage open, R is infinity, then this voltage is directly appearing here. So that is open circuit voltage. This is a short circuit current. Assume this port is shorted, then this voltage, dependent voltage source divided by this output impedance is just the short circuit current. Okay. So this is the equation for the inverter ellipse. So I plot that equation here. This x-axis is magnitude of this voltage, and y-axis is magnitude of this current. So I draw the ellipse curve. Meaning of this is, for the given operational condition, the operating point can be this point. It start out 0. If R is 0, then operating point is here, and point is moving through along this ellipse curve, and this becomes infinity. The point will arrive at this point. Right? So in the middle, you have distance value of R. Then you draw this line. Slope of this is 1 divided by R, because this dimension is not resistance, it's conductance. So inverse of this one is this line, and the intersection point Q is operating point. Okay. So for the given operational condition, you have this curve, and if this R value is fixed, then you have this curve, this line, then the intersection point is here, then this is the value of magnitude of this up voltage, and this is the value of magnitude of this up current. Okay? So this is the meaning of this ellipse curve. So we want to derive this equation. Okay, before that, I'll show this. This is a comparison of that curve compared with this PWM converter in CCM. So this is the PWM converter in CCM, that our voltage is always fixed. Okay, our voltage is dual ratio times this input voltage, this one, and that value is constant regardless of any change in this load resistance, as long as the converter is in CCM. So we restrict our interest only in the CCM operation. Then this is the load line. This is the magnitude of this one, which is DC in this case, magnitude of current, which is also DC in this case, and this is the load line. Okay, it's not an ellipse, it's not a curve, it's just straight, the horizontal line here, vertical line here. So if the value of the R is R1, then this is operating point, and I1 is given here. If you change this, increase or decrease, I don't know, but for different values, you have different values of current, but the operating point is on this one single point at this vertical line, load line. Okay, slope of this line This is the V, this I. Then slope becomes infinity. Slope becomes infinity. If you consider inverse of that slope, 1 divided by infinity is 0. Okay? So this is output impedance. So for this PWM converter in CCM, output impedance is 0, ideally. Okay? That means whatever value R might be, output voltage remain the same because output impedance of this one is 0. Otherwise, you have the voltage division factor here. Then that means the output voltage depends on this value. But if you have this 0 output impedance, then there is absolutely no zero loading effect. All right? So this is ideal case, which is the nice characteristic of this PWM converters. But for this resonant converters, situation is very different. So this is the ellipse curve. Okay. So operating point, if you have value of R1, then operating point here. You change this value to R2, another operating point, and you change further the other operating point. Okay. So this current is changing I1, I2, I3, and slope of this current. Actually, inverse of this is what? Output distance. The value of output distance is small, large, very large. Okay. So output impedance is considerably large. That is also a problem because there are substantial loading effect. So all the characteristics of this resonant converter highly depends on load resistance. Load. That is the real problem. Okay. Another one is this dependency varies with R. If you change this R, then you have a different situation, right? So there is a strong loading effect, and that loading effect is highly depends on load characteristic. Strong load-dependent loading effect is the characteristic feature of this resonant converter, very different from the case of PWM converter. Okay. So next step is we go through the derivation of this inverter ellipse equation. It's not difficult. Okay. So this is the situation. This is the Thevenin's equivalent model of inverter model of converter, resonant converter. So maybe you know this. This is the complex variable. So V1 plus J VT, real part, and imaginary part. So or this is the phasor representation of this complex variable, this magnitude and phase. Magnitude is this one, square root of V1 squared, V2 squared. So square of this is this. Then if you multiply this V vector and V star is the complex conjugate of V, then you have this. Then you factor this out, so you have this. So you have a simple equation relating the magnitude of this complex variable and this expression. This is the V and V star complex conjugate. So this is all known. So we start out this here. Right? This is the magnitude squared of this our voltage. So our voltage is this one divided by 2 impedances. This is also complex variable. So V star. This is not a star. Abstract something, not easy to pronounce, so I use star all the time. So this is the expression, and this is the complex conjugate of this whole thing. Okay, this complex conjugate is coming out in front. So H infinity and H infinity star, VS1 star, VS1 and VS1 star. And we have this expression, and this becomes the magnitude squared, and magnitude squared, we have this. All right, so we have this term remaining. Okay, here is the thing. So we assume everything is purely reactive. Then all the output impedance or impedance, this one will be purely imaginary. All right, so it does not contain any real component. Then suppose this is the GOO. Okay, this is the output impedance with input port shorted. Then it has imaginary number, so it has J in front, and this is the magnitude of that variable. So this conjugate star is, you just put minus sign here, right? So this simplifies a lot. If this is not the case, it is very complicated, and result will be useless. Very complicated. No any insight or no any useful information. But we assume this. So parasitic resistance are ignored. We assume they are very small to be ignored. Then this simplifies to this. Okay, so this, let's call it this A. This denominator is A. Then A is here. So this stop operation, this real number remain the same and becomes minus J is coming. Then you multiply out this. Okay, then R squared plus this magnitude of this GOO squared is coming here. All right. So the whole equation, the first equation we started out was this. This becomes this one. Okay, equation number 1. So we have V. We don't have any I here, but there is a relationship between V and I because we are assuming resistive load. This is the load line. You combine this and this all together and rearrange the equation a little bit. Then this is the equation. All right, this is the equation, very similar to the ellipse equation. It is ellipse equation. This is H infinity times VS1 is this VOC, open circuit voltage. And this open circuit voltage divided by short circuit output impedance is short circuit current. So finally, you have this equation. This is inverter ellipse equation. This is a very, very important relationship. And this relationship is very useful to analyze something. All right. So you may recall this. This is open circuit voltage. You divide the open circuit voltage by this GOO as a short circuit current. All right. Okay. So this is one thing. We derived the ellipse equation, and somehow we want to relate this ellipse equation to the condition of the maximum power transfer. Okay. So you know this for the this something is wrong here. Let me fix this. Delete this. Start with capital letter T. The maximum output power transfer is occurred, will be achieved when this R is output impedance, output resistance, short circuit output resistance. This is well known from the basic circuit theory. Maybe you studied this, you saw from class, something like that. All right. So when R is this one, this converter can transfer the maximum power. Okay. So we call it R match, and the value of R match is just output impedance of converter, output impedance of the converter, magnitude of that is the R match. We will deliver the maximum power. All right. So we all know this, and when this condition occurred, R is selected as R match, which is this one. That operating point is somewhere here, and this is the slope of 1 over R, and R is actually R match, which is the output impedance of that converter. Then this point, this is operating point, quiescent point, located VOS divided by 1 over square root 2. And this is the IOC divided by square root 2. Okay, so this is the point. If you select the R for the maximum power transfer, then operating point here, and this coordinate is this one and this one. We prove this. We will prove this. Okay. So first we prove this. This 2 point satisfies the ellipse equation. So if we put this, then this simplifies 1 over 2, 1 over 2. 2 of them is 1. So it satisfies the equation, this ellipse equation. So this point is on the ellipse equation. That's fine. And second step is at this equation, if you draw this line, then slope becomes what? R match. Okay, magnitude of GOO. You should prove that. So what I'm saying is this must be this one. All right. So we proved the first requirement and value at this point. slope at this point is this one divided by this one, and this is, we cancel this square root 2, and this becomes this. All right? So this is the definition of this one. So the relationship between open circuit voltage and the short circuit current is related with this magnitude of output impedance. This is wrong. This should be GOC. Okay, somehow I mixed C and XS. This should be GOC, VOC, and this should be VOC. VOC, not this one, something strange. Open circuit, short circuit, and this relationship is known. This is definition of short circuit current and open circuit voltage. ISC is V open circuit divided by magnitude of output impedance evaluate with input shorted, which is this. Okay, so we know this. This should be true. And load line equation is this one. This is the definition of the load line. That means this R should be this one. Okay, you have this equation, and this point is satisfying this ellipse equation. So this is the point, right? One thing or two things I'd like to mention is this is the point. That Q point is the maximum power transfer point, not necessarily the maximum efficiency point, or not necessarily the GBS switching point. Okay, it just indicates with this the power transfer is maximized, but we don't have any idea about the efficiency or any idea about the GBS, GCS characteristics. We need some additional information to judge that. Okay, so we'll step forward such analysis. Implication of inverter ellipse is shown here. Okay, so this is the inverter, Thevenin's equivalent model of the inverter, and we have this inverter ellipse. So this is R match, and maybe you select R, very small value, and go to R1 and pass this R match and pass R2 and go to infinity. All right, then operating point will travel starting out this point, and it terminates at this point. That is what this graph is saying. Okay, at this point, R match is here. Then magnitude of this voltage is this one, but we don't know anything about the efficiency of this circuit or GCS, GBS characteristics are unknown here. Okay, so main message here is inverter ellipse is unique, determined by H infinity, VS1, GO1, GOO. But that depends on switching frequency. Right? So this is not a fixed. If you change the switching frequency, this value will be changed, and this inverter ellipse equation will be changed. The shape will be changed. Right? So this it assumes this thing is fixed. Okay. Switching frequency is fixed, but it highly depends on input voltage. You are assuming this input voltage is fixed, and switching frequency is fixed. If you change that you have families of this kind of curve, and that will provide the large signal information, large signal operation of the converter. Okay, that's different business. The utility of this inverter ellipse will be shown in later sections. We will use this a lot, many times, to design the tank circuit and to analyze the tank characteristics. Okay, that's coming later. All right, so this is the end of section 6. So we move to section 7. Okay, this section is previous one was easy, right? This one is easier. Next one is more easier. Okay. Dependence of tank impedance characteristics on the load. Let me introduce this slide first. It is kind of the preview of the entire section, which is this. So this is the tank circuit, which is inverter circuit for the converter. So this is the input voltage, and this is the tank current, or it is called tank current. So many people call it transistor current, switch current, tank current. So I prefer calling tank current. So this is tank current, and GI is input impedance of this. So it's very easy because this is just a combination of the 4 passive component. So 1 over SC plus SLS, and this one parallel combination of this. All right? And this current, this I, is load current. And V is what? This is load voltage, out voltage, or out voltage, out current, right? So impedance seen at this input port is very important because the GI, okay? This impedance, magnitude of this impedance determines magnitude of this tank current, right? Tank current is just this one, magnitude of this one divided by magnitude of this impedance is magnitude of this tank current, okay? So knowing the tank current is very important, all right? The reason for that is we assume the switching loss is 0. We assume the GBS switching, so power loss from the GBS switching loss is 0, but still conduction loss is a problem. This IS, tank current, pass through this reactive component. Some of them will be this load current, and then it comes back through this, and there is a switch network. So in the switch inside of this bridge network, and pass some parasitic resistance in here will create the conduction loss. So conduction loss is very important. So we are only considering conduction loss in this resonant converters. We assume the switching loss is negligibly small compared to the conduction loss. Okay. So knowing this is very important because of that. With that information, you can decide this magnitude of tank current. Okay. All the tank current is not going to this path. Just part of tank current becomes the load current. Okay. So most of tank current is just circulating through this channel, just idling through this channel, but that current is required. With that, we have the resonance characteristics of this resonant tank. All right, that is provided the frequency selective bandpass characteristic of this tank circuit. All right, that provide GBS switching. All right, so maybe you remember this. When the beginning of this semester, I explained some of the resonance as the energy transfer between the capacitor and the inductor. That concept is not important anymore. You can forget about that, all right? You can forget about that and just think about this circuit behavior of tank circuit, okay? So many times the energy transfer between the inductor and capacitor, right? That does not help a lot. Sometimes that do some harm to you to understand this circuit behavior. So forget about that, okay? So that is related with resonant power conversion, basically, but that is not important at all now, from now on, right? Just to concentrate on circuit behavior of this. So you have interest about this GI characteristics when this thing varies from 0 to infinity, all right? So R is changing, and R is changing a lot. So consider this variation. R starts out from 0, and it goes to infinity, all right? So when R is 0, assume R is 0, then this is the shorted. Then you have this, just the series connection of 2 reactive components. That impedance is shown here. Impedance is shown here, all right? So you have just one resonance here. This is a curve with R equals 0, all right? This frequency, F naught, is very easy to figure out. So this is 1 over divided by 2 pi square root CLS. Okay, so with 0, this magnitude, right, this is the magnitude curve. Magnitude of input impedance is this one. So you increase R to infinity, so this is open. Then there is another resonance, but the this resonance across C, and this series combination of two inductors, which is this, okay, C and S plus LP is coming here, all right? So when R is 0, impedance curve is this, okay? This x-axis is what? This is the switching frequency, right? When switching frequency occurs here, that input impedance becomes 0, okay? Because this is 0, then it's showed it. When this, something like that, okay? When this becomes infinity, then resonance occurs here, all right? So with 0 resistance, this is the impedance curve at the different switching frequency. With R becomes infinity, you have another curve like this. What happened in between? You change this one from 0 to R, all right? Then input impedance will change, but they change in a very systematic way. This is the curve. So this was 0. You increase a little bit, then it's the second one. You increase further, then I don't know, maybe this one, increase further, this one, increase further, this one, and finally it becomes the infinity, then you have this, all right? That is the pattern of impedance. There are two curves. One is this one with 0 resistance, another curve with 0, with infinity resistance. Two curves meet here in the middle. They should meet somewhere, okay? This frequency, later on we evaluate this frequency. This frequency is given by this. So we call it F naught, F infinity, and Fn. There are three important frequencies, and impedance for the all cases are bounded by this curve. What I mean is, the impedance cannot go out like this. All impedance is bounded to this area. It passes through this and bounded this area. So it shows this kind of pattern. That is very nice, right? So from this impedance pattern, so we can judge many things for the given frequency, like this, Fs. Suppose you select Fs here, then when R is R prime, okay, maybe this is the relatively large value, then input impedance is this one, then this IS1. IS at the operating point 1 is given by this, so you know the magnitude of the tank current. Furthermore, you know this is GCS operation. No, this is the GBS operation. Because input impedance slope is positive, this is the inductive area. So at this point, the converter is in GBS. You decrease R to this one. This is the small R of 0. Then operating point is here. Then you can determine the magnitude of tank current by dividing this one by this. And you understand this is, at this point, it becomes the GCS operation, all right? So for the given frequency, if R is small, then converter is in GCS operation. If R is large, then converter is in GBS operation. Those kind of information is all shown here. There are many other good information, very important information, all right? So this region is what? This is GBS region, right? Because it has this slope, inductive slope, and this region, the converter is always GCS region because it has this capacitive slope from 0 to infinity R. During this period, converter can be either GBS and the GCS, all right? If R is large, R is large, then converter is probably in GBS. If R is small, then converter is probably GCS. Their information is shown here, all right? So change ER causes a substantial impact on GI characteristic, magnitude and phase, and this determines magnitude of tank current, which determines the magnitude of conduction loss, basically, and it also determines operational mode of this converter, GCS and the GBS operation. Okay? So this is some kind of preview. So we'll go step by step. Another illustration. All right. So illumination of GI pattern. Okay. I already explained the pattern of GI, but there is a theorem stating that. All right. Theorem number 1. If the tank network is pure reactive, no resistance considered here, then its input impedance magnitude is monotonic function of load resistance. This means if it increases with the R, it keep on doing that for the whole range of the R. Okay? If this R, magnitude of GI, is inversely proportional to R, and it keep on doing that. All right? So the meaning of this will be clarified later. So you understand this. Okay? Monotonic function of this. All right? So for the some band, this band, okay? This is the previous figure. So this is one frequency, F infinity, and another resonant frequency, which is F naught, F0. Okay? During this area, this R, this GI, magnitude of GI, is inversely proportional to this R. Right? So R is increased, GI is decreased in this region. Right? So every curve remains in bound two curves. Everything is inside of it. Okay? And that is the borderline. So in this region, GI is proportional to 1 over R, inversely proportional to R. Okay? The meaning of this is it won't change this pattern. Okay? When it goes, if this R is increasing, this will never go down. I'll show this later. This is opposite. All right? In here, this is R. R is proportional to R. If R is increased, then magnitude is increased. All right? It increased. It at one particular frequency, it never comes back. It never comes back. It keeps on increasing here. If it goes this way, it keeps on decreasing. Okay? It never go up again. Is the meaning of the monotonic function of the R. All right? So because of this, we prove this. Okay? We prove this using EET, external element theorem. Maybe some of you heard the term external element theorem. We prove that. So because of this is the pattern we predict. This is true. Okay? So everything is bounded between. So it starts R is 0 and R is increasing. And at particular frequency, if this magnitude of the GI is decreasing, it keeps on decreasing up to this point. If this is the other region, then if you increase R, then maybe GI is increasing, then it keeps on increasing at this particular switching frequency. That is the meaning of this. Okay? So this is very important. It provides very valuable information about the efficiency of this resonant converter. Okay? Their story is coming later. And I already said this. Okay? Part of said. This is a case. All right? So GI pattern and GVS, GIS characteristics, positive slope of GI magnitude indicate that you are in GVS region. Positive slope has you have GVS, and negative slope you are in GCS. Right? So from this sketch of this GI, for the all cases, from 0 resistance to the infinity resistance, and from this frequency, very low frequency, to very high frequencies. So from this information, if switching frequency is above this F naught, then you have GCS. GBS switching. If switching frequency is below this F infinity, you are in GCS switching all the time. In the middle here, and in this region between F infinity and F naught, F0, there are FM. Okay? FM, all the impedance magnitude is merging together at this point. We will prove this. Okay? We will prove this. The behavior of this is they should behave this way, mathematically. Okay? So it's not just a sketch. All right? Then in this region, if R is large is this, then you have what? GBS. If R is small, something like this, then you have GCS. All right? So GBS for large R. I use plural form, okay, but it confuses. Maybe some student will look for RS. There is no RS. We only have R. For large R's, we have GBS. For small R's, we have GCS. Okay, that is so obvious here. And this frequency, resonance frequency, F infinity, because this one is open, then so we have this, see this connection, and one is shorted, then we have only two elements, but somehow in the middle, you have this expression. We'll prove that later. Okay, so this is the story. Okay, so so this area is large R, right? So from the slope, we conclude this is a GBS region, and this is the small r region, then this is a GCS region. Okay, same is true here. So this is large R, this part is GBS, this is small r, this is GCS. Okay, and switching frequency is above this resonance frequency F0, then the GBS is guaranteed any value of the R. Opposite is true for this region for the GCS. Okay. All right. Another very important information about the efficiency, line node efficiency. Okay. A long time ago, I wondered why they are paying attention on the line node efficiency, okay, heavy node efficiency. I thought that should be important. This is the less important, but opposite is true here. I found out that later. Let me explain this. Okay, this is the tank, all right? So IS is tank current. This is load current, okay? Maybe I put IS prime here. IS prime here. Then IS is sum of I plus IS prime. And IS is load current. And this IS prime or IS is just circulating current. It does not contribute to any power transfer from source to load. It's just idling for the operation of this. All right. Suppose you increase this. Then I will be decreased, right? Because this R is large, then current will be reduced. Then you expect if this is reduced, this should be reduced, right? But opposite can happen. If you increase this, if this input resistance decrease like this, you increase the R in this direction, then this is decreased, but this GI is decreased. That means this circulating current, tank current is increasing. All right, that is bad because this tank current is contributing what? Conduction loss or not. Suppose this is R is infinity, then no power is transferred from the source to load, but this becomes very small here in this region. Then this current very large, and it is circulate. This is open, but large current is circulating through this tank. It creates a lot of conduction loss. That is the bad things, right? Because line node efficiency is very important. Some case, this show R of 0 or very small value, you have some value of the I, all right? If R is infinity or very large R, you have some value of small I. Then some case this IS remain the same. That is very bad. Without transferring any power, it just consumes the conduction loss. That is the tragic situation. Because of that, the line node efficiency is very important, more important than heavy load efficiency in the case of resonant converter. Okay, so people were paying attention on this, and when I was studying this for the first time, I couldn't understand immediately. Later on, I understand the whole situation. All right, so that the story I mentioned is written here. If GI is proportional to this 1 over R, not R, all right? Then for this case, you increase R. So you decrease R, it becomes 0 at this extreme point. Then GI becomes very small, the minimum value. Then this IS is maximized without delivering any current. It just creates what? Your converter is not working, still consuming a lot of conduction power. That is the problem. Okay. So with this, the low line node efficiency will be very poor. Right? So to avoid this situation, magnitude of GI should be proportional to R. Okay. For in this case, you increase the R, so this value is reduced, and also this GI is increased. Then this tank current becomes small. Okay. So line node efficiency will be good or better compared to the previous one. All right. So with this GI, magnitude of GI is in proportional to this R. Then you have good line node efficiency. This is the desired operational region. And you also want to maintain the GBS. Then this is desired region, operational region. But this region has some problem. We'll discuss it later, maybe after midterm test. We'll discuss that. That is related with the dynamic characteristics of this converter. Maybe you may want somewhere here, something like that. Okay. So if you go down to this direction, it will suffer this poor line node efficiency because of that dependency of GI over 1 divided by R, inversely proportional to R is the bad one. Okay. So those conduction nodes due to the large IS will be large, yielding a poor line node efficiency. Okay. If GI, magnitude of GI is proportional to R, like this region, the large R with small I load current, and it is involved with small IS because of the large GI. All right. So condition for good line node efficiency is magnitude of GI gotta be proportional to R, but there are many cases, right? The other way around. All right. So you should understand that. You should understand this. Okay. So maybe this is the same idea as the previous one. So you understand this, right? Very important, right? You may need this. Initially, I intended to write down something, but I already explained that, so you should remember that. So line node efficiency and operational mode. If converter operates under the condition of this is this region, right? With poor line node efficiency, you should avoid this operation. Still, but below this frequency, the converter is in GCS operation, and in between these two resonant frequencies, for the large R, you have GBS, and for the small R, you have GCS. But this above this F0, okay, this resonant frequency, you have good line node efficiency and the GBS characteristics. Okay, so maybe this is the desired region for your converter. Okay, so I wrote down here. So some case when this is the infinity, the converter is just dissipating power without delivering zero power transformer. This condition, the conduction loss at the low load condition can be as large as that of the full power load. This is stupid. Without any power delivery, the conduction loss is the same as the case of full power delivery. That is the ridiculous. Okay, we cannot accept that. Right? So for this is the specific example of LLC converter. Okay, for the LLC converter, what will be the desired operational region? This region. Above this region, okay. Maybe try to answer this. So I'll give you 4 choices. first one is this area 1. The other one is this region. Third is this region all combined like this. And final candidate will be somewhere here. How to answer, right? I'll give you this answer to this question sometime later. Okay, maybe a couple of weeks later, I'll provide the answer. All right, that is not easy question. All right. So in some sense, maybe you prefer this 2 or 1 or 3, 4. Okay. But you should have the further knowledge about the operation of this resonant converter to answer to these questions. Okay? All right. Proof of this. Okay. Proof is coming here. You need this. Extra element theorem is from the guy from the Middlebrook, who is, I call him the father of power electronics. And he proposed this extra element theorem. Okay, so this is the summary of extra element theorem. Last semester, I spent the whole semester talking about the extra element theorem and in the application of DC power distribution system modeling and analysis and the design of DC power distribution system. That lecture was entirely depending on this extra element theorem with many variations. Okay, so this is the simplest form. All right, think about this. This is linear network. Okay, this is input and this is output. Maybe you are interested in transfer function from input to output, transferring from the input to output. Right, and this is the system. And there are something here. So initially this G was inside of this box. But I take out here. So I extended this G to here. All right. So this is the same representation and simply modified to explain the meaning, implication of extra element theorem. Extra element theorem means this is the circuit theorem related with extra element. Right? So we consider this extra element. So I pulled out these two branch and I pulled out this impedance element here. That was originally there. Okay? But with this is the definition of extra element theorem. H is transfer function gain of interest, maybe input to output transfer function with everything included, which is very complicated. Maybe this is very complex. Okay, assume this is some strange part, very complicated part. So we want to avoid some complication. So we initially take out that part like that. That is one thing. Another is sometimes this is some element, circuit element, or some functional block, impedance that is not defined yet or unknown. We don't know the inside of this box. That will come to later. So until everything is finalized as assembled as one complete box, then we don't have any information about that. Okay? We know there is this functional block, or we don't know inside of this, then take that out. Right? So there are two cases. One is this one is inherently complicated, so we don't want to take out this and simplify our analysis. Then is one point. And more important point is this thing is unknown here. Maybe it will be known later. Okay? So first we analyze the system without this, and later on we incorporate the impact of that element later. Two-step approach. Okay? That is also important. So there are two main applications for the EET. Another one is shown here. To prove something, we intentionally use this form. Okay? For our case is the last one. To improve that, the behavior of input impedance of resonant converter, we'll adopt this theorem. So let me explain the theorem. Okay. G is the impedance of a circuit component, which is located here. It was originally inside of the box, but we take out like this, okay? Located these two terminals, and we call it extra element theorem. Maybe we assume this is absent in the beginning, and we think it is re-invited later, something like that. So extra element, term extra element is originated, that feature. So with this original transfer function from the input to output is expressed like this. This is H infinity, and this is the 1 plus zeta bar divided by G, and 1 plus G bar divided by G. G is impedance element, all right? So you have this expression, H infinity is transfer function from input to output with G infinity. Means is open circuit. G is not there. We ignore G. Is not there. All right? G is take out. So this is with this thing open, or assuming this is infinity. So we evaluate input to output transfer function with the assumption of this. Then your job will be much easier. Right? And then you have this, the additional terms. One is this, and this one is very easy because this is the impedance G. Originally identified impedance. All right. One thing here is with this H becomes H infinity when G is infinity, right? Because when G is infinity, then this thing becomes 0, 0. So this becomes 1, then H and H infinity, the same, right? So H infinity is transfer gain H, evaluate with extra element G removed, and we call it open circuit transfer functions. Right? There are two impedances. This zeta bar and the G bar is impedance looking into this through this port. Okay, so you are looking into this through this to this box, and this is the driving point impedance. Maybe you put current source here, then measure voltage across it, and the ratio, find the ratio between them. That is what? Driving point impedance. Evaluate at two different conditions. One is this one. This one is easy. This one is easy. Okay. So G1 bar. G is what? G is impedance element, and small g bar is driving point impedance measured through this point with the condition this input variable is 0. Okay. So originally this is the input of this transfer function. This is output of a transfer function. First assume this is 0. So this port is connected to the ground, and you evaluate this driving point impedance seen through this path is that is the G bar. Okay. And another one is this is a very tricky one. People call it null driving point impedance. Assume somehow this output is reduced to 0. This is the 0. This input is not 0. This is a very strange situation. There is an input, but this output is 0. Okay? Very special condition. This condition is output null condition. Null means 0. Okay? Null means it becomes nothing. All right? So output nullified condition or output null condition. Under this condition, you can still evaluate the driving point impedance looking into this path as named as null driving point impedance, and it's called G bar, zeta bar. I'm sorry, this is G bar, this is zeta bar, right? Not easy. This is a conceptual illustration, all right? Okay, previous semester, me and my student all struggled with this problem. Okay, it's not new one. This is proposed by Hendrik Bode, the guy, you know, that Bode is that Bode. Bode plot guy. He proposed this maybe 1940s. Okay, their theorem was that nobody was using that, and later on the Middlebrook, the father of power electronics, he dig out that theorem in late 70s, and applied these things to the introduce this theorem to power electronics, okay, which is very significant contribution to power electronics. Okay, so proof of this thing for the general cases, maybe this extra element, we have one extra element. This theorem can be generalized to two extra element, 3, 4, infinitely many extra theorem. So general proof of this general theorem is very complicated. Okay, we should use the matrix determinant theory. It's not a simple circuit analysis technique. It has deep mathematical root. Okay, circuit analysis technique. But you are using this in simplest way. Just we assume one extra element here. Okay, this is the expression of Middlebrook's extra theorem. There is another form, alternative form. Everything is very similar, but in the case, in previous approach, we initially assumed this is open. Here, we initially assume this is the shorted. This is shorted, and we apply this. So we have this expression. I delete these things. I use the same slide. I just modified by deleting these things. So here we have H0. This is the transfer function. Evaluate with this G becomes 0. We showed you this, and with the simplified circuit, we easily derive this, and we have same G, same zeta bar, and same G bar. All right? But this time, this zeta, G is in the top, on the top. All right? So when H becomes H0, when G is 0. Right? So when this thing is 0, it becomes 1, then H and H will be the same. Okay? So this one may make sense. Otherwise, something is wrong. All right? And H0 is transfer function H evaluate with extra element G shorted. Okay? Called the short circuit transfer function. And this zeta bar, G bar, zeta bar remain the same. Okay, the terms remain the same. Output null condition and the null driving point impedance. All right. So with this, we prove theorem number 1. Okay. So we need this. This statement of theorem number 1, original statement of theorem number 1 is a monotonic function of something. Okay, it says the monotonic function of load resistance are either this one or this one, either this kind of trend or this kind of trend. Okay, that is the original statement, and modified statement is same as the essentially same as the original one, but in different form. Okay, as shown here. For purely reactive tank networks, their input impedance GI, magnitude curve, is bounded by two impedances. Each one is GIO, short circuit input impedance. Okay, input impedance evaluate with R becomes 0. Right. Another one is GI infinity, which is input impedance evaluate with R of infinity, open circuit input impedance, short circuit impedance. The same thing. It's the same statement. Maybe I show this. Okay. This all the impedances are bounded between two curves. This is GI infinity. This is GI 0. Okay. So all the impedance is bounded in between, and they come all curves come together and move this direction, and this but trend has been changed. Magnitude is decreasing with larger R. Magnitude is increasing with larger R. They pass this channel, narrow channel, and this boundary. Okay? So this is the same statement. So we prove this. It's not difficult because we know the ET. So GI is input impedance. Seeing the input port of the tank. So it's ratio VS divided by IS is the GI. So GI is expressed like this using the ET. It's the same expression, but different form. This form is much complexer than this, but it provides a lot of information here. All right? So we have this, and originally it is R, so R is here, and this zeta bar is, first this one, this GI infinity is the input impedance with R being infinity, open circuit, okay? So you evaluate GI with open circuit, then you have this, and the R is this one, and zeta is the driving point impedance seen by this point, one with Vs equals to 0, the other one with Is equals to 0, okay? Second one with Vs equals to 0 will give you this, with Is equals to 0 will give you this. So anyway, this is the expression. We're not going to evaluate this. We just use expression of this. So this is the GI infinity, open circuit impedance, and the zeta bar is null driving point impedance with Vs equals to 0. This is the definition of null driving point impedance. So Vs is 0 means input port is shorted. This is the output impedance seen by output with input port shorted. Okay? And the G bar is with Is equals to 0. Is equals to 0 means this is open. Right? So this G bar is output impedance through this R port, through this load resistance with input port open. Okay? So this is the first expression, and this is the second expression. So we have two different expressions for the same thing. Okay. This one. Oh, no. That was the same expression. I'm sorry. This one is the same expression. We just specify this. You have another expression. We have two versions of ET. The second version of ET. So this is the relationship. GI can be expressed like this in the first ET form. And with the second E form, we have another expression. Later on, we'll use this to prove something. All right? But now we just use this part. Okay? Then we evaluate magnitude of GI. Okay, let me. You repeat this tomorrow, but I'll guide you some highlight of this. So we have this. Okay, this is the equation, and we evaluate the magnitude of this. We evaluate the magnitude of this complex variable or vector, which is this. Okay, so GI times GI star, and this has this expression. So this is the expanded version of this. You have this one in front and this one in front. Okay, but this is the purely reactive resonant tank circuit. We have a special relationship like this. GO0 is J, right? Suppose this is imaginary, only imaginary. So you have J and magnitude. Then complex of this thing is just change the sign of J. Same is true here, J minus J. Then this calculation simplifies, right? Because this thing simplifies. So we have this expression, this GI magnitude squared is like this. Okay? We differentiate this because we have some inflection point. To find some inflection point, so we differentiate this. You know this is a differentiation of division of two functions. So you have this formula. With this is the conclusion of this. This is the differential version of this. So we have this. Then if differential value becomes 0, then trend is changing. Okay, something increasing is decreasing, then you have a derivative or something that will be 0. All right? So we have three zeros. One is 0. Okay, if R is 0, whole thing becomes 0. Another 0, which is if R is infinity, here we have one R, we have R squared for something. So at 0, we meet this condition, and we meet this condition at 0. We have another point, which is this point, if this value, they become same, then the whole thing becomes a 0. Okay? We have a 3 point, 0, infinity. Okay? There is no point in between. Okay? So from 0 to infinity, the trend won't change. Okay? That is one thing. At this frequency, when magnitude of this thing becomes the same, the trend will be changed. Right? But so this one is related with output impedance, but there is some theorem. They call it reciprocity identity. There is a relationship like this. This one. Ratio of this is ratio between output impedance, ratio between input impedance becomes the same. We prove this tomorrow. Then you have this derivative becomes 0 point at 3 different points. One is out of 0, out of infinity, and one of this special point here. All right? So in between, from R 0 to infinity, there is no inflection point. Okay? There is no point where the derivative of that thing becomes 0. There is no point. The trend is changing. Means you have this. Right? Because from 0 to infinity, this decreasing trend won't change. From here, from 0 to infinity, this amplitude increasing trend won't change. So they should be bounded in between. All right? And this is the one critical point. Here, this derivative is 0. So this value is independent of the R. Means all of the curve should merge together at this point, at this particular point. Or the easy way of seeing this is somehow only this region is allowed to be this curve, right? So curve, it should pass this point to move the other region. Otherwise, it cannot go like this. This region is prohibited, mathematically prohibited. Then this should pass this way. Then this is the typical shape of input impedance magnitude curve. Right? You understand this? Okay? And this is very simple, but the significance of this is very significant. Many valuable information is coming here. Selection of the switching frequency. Understanding of the behavior of this resonant converter. Okay? Resonant converter is not easy to understand, basically. Right? This PWM converter is man-made topology. This is a natural one. Okay? So everything is natural in resonant converter. In PWM converter, we chop signal. Okay? There is no chopping here. Everything is smooth. Then the price you should pay is you should understand the behavior of these things thoroughly. Okay? So otherwise you will be lost during the design process. Okay? So you cannot design the tank, you cannot design the controller without the solid understanding about this general behavior of this complicated, natural or God-made circuit. Okay? Okay. We repeat later part tomorrow. Okay, thank you.